Let us now look at some constructions with sheaves of modules and pre-sheaves of modules. So the first natural thing to consider maybe is the issue of kernels and images of maps. So let M and N be two sheaves of modules over a scheme X, and let F from M to N be a morphism between them. So remember that this gives us a map Fu from M of U to N of U. That is a module homomorphism over the ring OX of U, and this is compatible with restrictions. So first, the kernel. The kernel is in fact a sheaf. So what does this mean? So we want to define a gadget that for each open set U gives us the set that is the kernel of the map Fu. So Fu is a homomorphism of modules and its kernel is well defined. And this turns out that this is a sheaf of OX modules. So it is clear from module theory that the kernel of each Fu is a module. And because F is compatible with restrictions, this will be a sheaf or a pre-sheaf of modules. We have to check that it is a sheaf. That's the non-trivial part, to check that if we have two elements in the kernel, or rather two elements in the kernel on some open subsets that agree on intersections, then they glue together to something in the full kernel. So let Ui be an open cover of U, and assume that Mi belongs to the kernel at Ui. So this means in particular that Mi sits inside M of Ui. And what we know is that Fui of Mi is 0 because it's in the kernel of that set. Now, because M is a sheaf, we can glue together these Mi to one M. So there exists M in M of U. A priori, there is no reason why this M should lie in the kernel at U. So we need to check this. So we need to check that F of U on M is 0. But this is enough to check on the level of Ui's. This is because the module pre-sheaf N is a sheaf. So if something is equal to 0 on these Ui's, this will glue together to 0 on N of U globally. And this is nothing but Fui of Mi, which is 0 by assumption. So the kernel is indeed a sheaf. It has the gluing property because checking that something gets sent to 0 is a local check. Being sent to 0 is a local property. We get a similar construction for the image. So the image pre-sheaf is defined as Im' F of U, being the image of the module map Fu in complete analogy to the kernel. And again, because of compatibility of F with restrictions, and because the image of a module homomorphism is a module, a submodule of N of U, this will be a pre-sheaf of modules. But this time it will not be a sheaf. To see morally why this is not generally the case, what does it mean to be a sheaf? So if again I have an open cover UI, so of U, and then if something belongs to the image, then on UI, then maybe I say that Ni belongs to the image of F on UI. So this means that Ni is equal to F UI of some Mi. But there is no reason to expect why all these will glue together to the image of one and the single M. So I can glue together these Ni to some N, but it is not in general true that this is Fu of one and the same M. To see how this fails in practice, we can take a specific example. This example is a bit technical, so if you feel that you do not need much further convincing that the pre-sheaf of the image is not always a sheaf, you can skip ahead. But in this example, take the inclusion from the affine line to the affine plane in the first coordinate. This corresponds to a map I star from O here to the push forward of O of A1. And this map simply can be thought of as the second coordinate is mapped to 0. So if you have a polynomial x1, x2, this will be mapped to the polynomial of x1, 0. That is roughly the idea. And then now if we take U as A2 without the origin, take U1 to be the set where x1 does not vanish, and take U2 to be the set where x2 does not vanish, then the intersection is of course the set where neither x1 nor x2 vanishes. So if I take this map as my map, then you can check that F of U is the whole polynomial ring in the first variable. F of U1 is the localization of the polynomial ring in the first variable. F of U2 is 0, and F of the intersection is 0. Why is that? Well, F, so here on U2 and on the intersection, we are localizing, among other things, with respect to x2. But in this map, in the image, x2 is set to 0. So when we localize with respect to 0, everything vanishes. But here, nothing much happens. And so, for example, the functions 1 divided by x1, this is in the image of U1. and 0 is in the image of U2. Both agree on the intersection because the intersection is the trivial module. So they agree in f of U1, U2, but they do not come from one and the same global function. So therefore, this is not a sheaf. They clearly do not extend to something that is defined over all of U. So what one does is one applies a process called Chiffification that to each pre-sheaf associates the best approximation of this pre-sheaf by a sheaf. And that sheafification of the image pre-sheaf is called the image sheaf imf of f. There is a separate recorded lecture on sheafification that could be a good time to watch now so that you understand exactly how the process is done. The idea that this slide gives is that when you make constructions on sheaves, sometimes you are lucky and you end up with a sheaf right away. If you don't, no worries, there is a universal way to do this through sheafification. So you do the thing you naively want to do, it will give you a pre-sheaf, and then you sheafify that to get a sheaf. So a morphism is called injective if its kernel is trivial, and surjective if the image is the whole target. So if it's a kernel, if it's injective, this means that M of U injects into N of U for each U. For surjectivity, one has to be careful because now the image is not the naive image. So since we have sheafified, there is something mysterious going on between the image and N. So one cannot straight away write down surjectivity in terms of open sets. So if you have an injective map, then by what I just said, you can view M of U as a submodule of N of U for each U. And so you can take the quotient module M of U mod N of U. And this is in general not a sheaf, it is a pre-sheaf. So by sheafifying it, you get what you call the quotient sheaf. And in a similar vein, we want to define the dual sheaf. So we know what the dual module is. So the dual module of M of U for any given U is precisely the homomorphisms from the module to the underlying ring, or the base ring, so to speak. And so we can define the pre-sheaf that to each U maps this thing. This will in general not be a sheaf. Sheafifying, you get the dual sheaf. Now, another important notion is the notion of exact sequences. And this works as for modules. So an exact sequence of sheaves of modules is a sequence with mi, that are modules, sheaves of modules, numbered increasingly, and fi going between mi and mi plus 1. And this is called exact if for each I, the image of fi is isomorphic to the kernel of fi plus 1. This needs a little bit of unpacking. So first of all, what we require is that the composition is the zero map. Then this implies, as an exercise, that we get a morphism from the image pre-sheaf to the kernel sheaf by direct construction. And now, because sheafification is as great as it is, this guarantees that there exists a morphism of sheaves from Im_fi to Ker_fi plus 1, because any morphism from a pre-sheaf to a sheaf defines uniquely a morphism from the sheafification to that sheaf. And this is good because this first morphism is not mysterious at all. The requirement that the composition is 0 exactly says that the image of fi on each u sits inside the kernel of fi plus 1. So this is really inclusion on the level of each u. So something that's very concrete. We have the image fi of u sits inside the kernel of fi plus 1 on u. But then to guarantee a sheaf morphism, we use the sheafification. And then the second requirement is that we require that this thing is an isomorphism. So this defines for us what it means to be an exact sequence. And one can show that exactness of a sequence is equivalent to exactness after reducing to any open subset. So by reducing, you get a sequence like this. And the original sequence is exact if and only if this sequence is exact for any open set U, if and only if this sequence is exact for any open set U in a given open cover. And you can also do this on stalks. So this is exact if and only if the corresponding construction on stalks is exact. That is a good thing to know that we will not prove specifically here. Some other important constructions are those of direct sums and tensor products. These are well-known constructions for modules, so let's extend them to sheaves of modules. The direct sum is not problematic at all. If you have two sheaves of modules, then the naive direct sum defines a sheaf of modules. This is almost immediate from the definitions, and because of how the direct sum behaves, if we have an element of the shape m plus n, or say mi plus ni on ui, then because we can glue together the m's to some m and the n's to some n, then we can glue together this to some m plus n. The tensor product is a bit more problematic. So we define the tensor pre-sheaf with this asterisk in the naive way by taking the sort of local tensor product one open set at a time. But in general, this is not a sheaf. To see an example of why this is not a sheaf, let m, so let x be P1, let m be the twisting sheaf with d equals 1, and let n be the twisting sheaf with n equals -1. So these are quotients of polynomials, homogeneous polynomials, where the denominator has 1 degree lower than the numerator. Here the numerator has degree 1 lower than the denominator. And so if I take, for example, if I take the open set, say U0, so this is the set of all points x0, x1, where x0 is not 0. And the same for u1. So I have the sets ui here. Then I can define the following functions. So I have x0 tensor 1 over x0. This belongs to the tensor pre-sheaf of u0. And I can define x1, 1 over x1 on u. And these two agree on the overlap. So on the overlap, x0 times 1 over x0, what I do is I multiply by x1 divided by x0, and here by x0 divided by x1. So these two terms cancel each other, and because I am tensoring over the algebra OX of u, these both belong to this algebra because the degree difference is 0 and they're homogeneous numerators and denominators. So by properties of the tensor product, this is equal to this. I have just multiplied by an element and its inverse on either side of the tensor product. And now I just simplify. So I get x1 tensor 1 divided by x1. So this is the case on the overlap. But if this were a sheaf, then therefore there should be one such non-zero element in the global section, so globally. But globally, n of P1 is trivial. This is a property one can show, namely because there is no globally defined function with a denominator that is not constant, right? So these, if there were such a thing would be of the form g divided by f, where f has lower degree than g, but there is no such thing defined globally on P1, so this cannot happen. So in general, this is not a sheaf. We sheafify to get the tensor product. And these two constructions conclude the constructions that we want to make on sheaves of modules, some with sheafification and some that turn out fine without sheafifying at all.